Started.
Hello? Okay, great. So we stopped at this example, which is very simple and straightforward, similar to what you covered in 520. You have here single machine infinite bus system where all these reactances are given in per unit, and if the machine is delivering power of 1 per unit, and both terminal voltage of the infinite bus terminal voltage is here. This is the terminal voltage, 1 per unit, and also that of the infinite bus is 1 per unit. Assume a three-phase to ground fault at point P. The fault is cleared by opening the circuit breakers at each end of the faulted line. What we need is to develop the power angle equation pre-fault, during the fault, and after the fault. So the first step is to find the internal voltage and its angle. This is what we need at the beginning in order to write the power angle equation, which is B equal to E prime V over X E sine delta. So this is the equation. So we need to find E prime. And the E prime doesn't change whether we have a fault or without fault. The E prime depends on the flux. And this flux, we assume, but this is not very much accurate. Later, when we go deeply in synchronous machine modeling, you will find out that this E prime will also has some dynamics, and it change also the E prime here. But for this transient stability problems, we assume that the E prime is constant, the flux is constant, and we rely on this equation. You probably know the internal voltage of synchronous machine is 4.44 times the frequency flux times the number of turns per phase. And of course, we have here the winding factor, distribution factor, and the Cording factor. But this is not the problem here. We assume the flux is constant. This very short time, 1 cycle, 2 cycles after the fault, and we assume that E is constant. The flux control loop here has a time constant of like 6 seconds or 4 seconds. So we assume the E prime is constant. So the first step is to find the E prime, and then we can see what is the power angle in pre-fault, during the fault, and after the fault. The main contributor here for the differences in the power angle is the configuration of the system. How to calculate X12. So this is X12 differentiate between pre-fault and during the fault and after the fault. System configuration changes, and then we have to get the value of X12 at each condition. So as we mentioned, you have the power transfer is 1 per unit between the terminal voltage is given here 1, and we assume it angle gamma, and the voltage here is 1. We assume it our reference is angle 0, and then we can choose the infinite bus as our reference. In pre-fault condition, steady state, we have the reactance equal to between the V terminal and the infinite bus equal to 0.3. So we can write the equation B equal to the voltage here times the voltage here over the transfer reactance sine alpha. So we can get alpha, so we can get the angle of terminal voltage with respect to the interference, which is the V bus, V infinite bus. So with this angle, and the voltage here is known completely, and the voltage here is known, and we know the power here, and we know the transfer reactance, so we can calculate the current. And current equal to Vt minus V infinity over the reactance. So you can calculate the current, and from the current you can get the E prime. Okay. Who's we need to invite him. I don't know who's this.
I have sent the invite.
Who?
Captain Abdullah.
I don't know.
Doctor, he's one of the students. Can't join.
He cannot join?
No,
I think he has some problems. He sent a message in WhatsApp.
So can anybody invite him or?
Done.
Huh? Done?
Yeah, he's here.
Okay. What's the problem with them? You couldn't log in? Or what?
I didn't know it was like this.
Okay. Yes. So, of course, you can get the E prime as the magnitude and the angle. So this is the steady state angle, 28 point something here. And this is becomes the, in pre-fault, this is becomes the bar angle equation. This is constant, this is also constant. In pre-fault, this is the reactance. So sine delta, this gives you the, for a specific operating point, for the initial operating point, the angle is 28, but this is for a specific operating point. In general, this is the bar angle equation in pre-fault. Definitely, in a steady state, you can write in B electrical equal to B mechanical, and this is at steady state. So B mechanical from the steady state condition equal to 1 per unit. So during the fault, when we have a three-phase fault here, how to develop the power angle equation? This is constant. This is also constant, but this is not the same as pre-fault. So we have to find out how much the transfer reactance between E prime and V infinite bus. We assume that, and we have here short circuit or solid connection here. So this is usually for such a simple system, we can use this, as we mentioned earlier, Y delta transformation, series parallel combination, and so on. And you can use simple techniques in order to find the transfer reactance between this and that. And this will be, this is 0.2 here. So this will be come here to, and this is will be with this bus 0.2. These are in parallel, so they will not play, this one will not play any part or any role, but with this one and this one and this one, you will convert them to delta, and then you can find x12. x12 here will be equal to this one, which is 0.3, plus this one, which is 0.4, plus 0.3 times 0.4 over the other impedance, which is will be 0.2 here. So this X12 will be, we have here 2.6 and 0.7 يبقى 1.3 per unit. So this is by Y delta transformation. But this is for very simple circuit, very simple configuration. You can implement this. In a systematic way, you can do the following. In a systematic way, you can build the, you can convert all these impedances to admittances, and then you form the Y bus matrix, which is easily can be done easily like a load flow. You can have this Y bus matrix, and then you can convert it to Z bus matrix, which is Y bus inverse. Okay, but before doing so, we can eliminate, in order to get the transfer impedance, we need to eliminate all buses, and this is generally the case for multi-machine system. If you have several generators here and there, and you have several transmission line connecting all these several buses here, what we will do is we build the Y bus, and then we can eliminate all the buses except those of generators. And if we have here 4 generators, 1, 2, 3, 4, so we will do Cron reduction as you studied it in 520. You can, by Cron reduction, you eliminate all buses except those of the generators. In this case, you can find what is X12, what is X13, what is X14, and so on. So this is what we will do here. This is a systematic way to find the transfer reactance. We have here, this is a bus, and this is also a bus. And we can, if the fault occurs here, we can assume that we have a fictitious bus here. Okay, and this is the bus here, which is connected to the ground, three-phase short circuit here, or three-phase fault, solid fault. If we have fault impedance, we have to incorporate it here, and we can also handle this very easily. So in systematic way, you can have it, you convert it to Y bus or to admittance diagram, and then you can form the Y bus matrix. The values shown are admittances in per unit. You have here, this is 0.2, 0.1, so this is 0.3, 1 over, it gives you minus 3.33. This is 0.4, minus J.25. We have here 0.2, J.2, minus J5. We have here J.2, minus J5. So this is the admittance diagram, and then we can, form the Y bus matrix for this 3x3 matrix, 3x3 or 3 bus system. So you can have Y bus, Y11, Y12, and so on, and you can easily form this, and you can easily get a Y bus as such. And then we need to eliminate the which bus we need to eliminate. And for this example, and as we mentioned here, and if we have multi-machine system, we need to eliminate all buses except those of generators. So if we have such system, very simple system, which bus we need to eliminate? Any answer? Ahmed, Sulaiman?
Yes, Doctor. Bus 3.
Bus number 3. We eliminate all buses except those connected to the generator. Bus number 1 and the bus number 2. So we need to eliminate the bus number 3. Can we, by Cron reduction, eliminate this bus? Can we convert this to 2 by 2? So of course you can do Cron reduction. This is a pivot element. and then you can modify these elements. This is the old one minus this times this over this value, this times this over, this one would be 3.3 times 2.5 over minus 10 point something. And then you can also have this, by Cron reduction, you can easily eliminate bus number 3, and we end up with y bus matrix equal to this. And then you can convert to, and you can have here y12. So this is y12, which is the transfer admittance between 1 and 2. And this is the transfer admittance between 2 and 1, which is done, of course, it will be a symmetric matrix. So this is y12. So you can have the electrical power equal to E prime V infinity over X12 or times y12 sine delta. So you can multiply and then you can get the this value. In pre-fault, this is the power angle curve. What do you think during fault, above or lower than this one?
Lower.
Lower. So this is pre-fault. This is during fault. So if we remove the next step, if we remove this faulty line, so where is the curve of the post fault? Region 1, 2, 3. Can you, Ayub?
It will be in region 2.
In region 2. So we expect that post fault, the power angle curve will be as such. This is the post fault, definitely will be lower than the pre-fault. This is the based on this switching scenario. If the fault is cleared by itself, sometimes the fault can be cleared by itself. In this case, we will go back to the pre-fault condition. So post-fault will be equal to the pre-fault if the fault is cleared without tripping the fault line. So for after fault, this line is off, so we can easily get the transfer reactance between this. So, and the power angle will be as such. So these are the curves, power angle curves, during fault, post fault, and pre-fault curves. So in more complex systems, of course, Y delta transformation, this simple reduction is not applicable. But the systematic way is to find the Y bus matrix, and then you eliminate all buses by Cron reduction except those of generators. Okay. And BM is constant in all cases. BM intersects the steady state case of A. This BM is constant here, 1 per unit, and this is found from the pre-fault condition, steady state. So as you can see here, the angle initially, the angle was 28.44. This is the system was working here. Can we on this configuration, on this figure, can we trace the operating condition or the operating point of the system? And for example, system is operating here at steady state. Everything is fine. Now we have fault. So this point will move. Will move where? how this point will move if we have a fault. Let us say this is point 1, and I don't make the figure very crowded. But if anybody want to answer this, where this point will go under this scenario, we have a fault at the midpoint, and then we clear the fault, and so on. And where is the final destination? Let me ask you, where is the final destination before tracing this point? But where is the final destination of this point?
On the curve, the post curve.
Should I move right, left, up, down?
Right.
Right. To this point?
Yes.
Yes. This is the final destination. You are right. This is the final destination. So how this point will move from here to here? Any answer?
It will move to the lower curve first before moving to this middle curve. Yes.
Okay. Then we reach here. Now we are here. Next.
Then it will to the right it will be aligned with the right one. Yes, here.
Here.
Yes.
And then
up.
طيب اوكي. يعني الجزء الاخير ده مش يعني not accurate, but let us see who can correct this. هل البوينت دي will jump directly to this one? يعني this point, when it comes here, it will jump directly here. يعني الجump دي means what? يعني this jump means what? Means ان احنا we isolate the fault. We trip the line. مش كده ولا ايه؟ عشان ينتقل من البري او الديورنج فولت للبوست فولت معناها انه اللاين ستريب. Am I right?
Yes.
طيب tripping the line. How do you match the line is stripped here at this point? And these curves is these curves are developed without knowing the fault duration. يعني الفولت for 6 cycles ولا الفولت sustain for 10 cycles ولا 1 second ولا طبعا 1 second is very long. يعني 6 cycle 10 cycle or 20 cycles. How do you know there is a match here between this point and the fault clearing time? No, actually, this point will move. Okay, and this movement will be governed by the fault duration. الفولت occurs مثلا for 6 cycles, so we are here مثلا. If the fault sustained for 10 cycles, then the angle will increase more and more. So we are here, right? Once we clear the fault, then this jump will come. Assume that we clear the fault here. We clear the fault here. When we clear the fault, what will happen? طبعا this is acceleration or deceleration. The machine here will accelerate or decelerate. Ramadan.
It will accelerate.
Why? B mechanical
Is higher than the B electrical.
is higher than B electrical. This is B electrical during fault. So we have acceleration. So when we clear the fault, we have inertia of the machine, and the machine is accelerating. When we trip the line, now B electrical becomes greater than, oh, okay. When we clear the fault, then B electrical is greater than B mechanical. So the machine will start to decelerate, but the angle still increases due to the inertia. The angle will go for some time here, increases. And then since we have a deceleration, so the angle start decreases again here. And it will not stop here due to the inertia, it will continue. Once it's continue, it will accelerate again. So the angle will go up here, and then it will come down, up, down, until it will reach here. And this is what we doing in time domain. This is the time, and this is the angle. So the angle will increase and decrease, increase and decrease until it reaches to its final destination. So this is what will happen exactly when we have a fault and we clear the fault. So this is the scenario. Do you have any question?
Yes, doctor.
Yes, please go ahead.
Yes. In the before now, you draw in the curve you draw before. We identified 3 regions between which the new point can be after fault is restored. Okay, so we identify region 3, which is above the pre-fault condition, which is above pre-fault condition. So we are region 3, yes, up. So okay. Is there any circumstance under which the point can move and we have a new curve above the normal operating condition after the fault is restored?
If I understand your question, you want to say, is there any scenario that we have the post-fault
yes
higher than the pre-fault?
Yes.
Actually, no, unless you have another switching of series capacitor or static var compensator, or you insert another device in the system. Now, just by tripping the line, definitely you will be lower here. Is it clear?
Yes.
By tripping the line, definitely you will be lower, and the impedance will be higher. Now, if you trip the line and at the same time you add a capacitance here in series, so in this case you have bigger value. But this is not.
Doctor, if you look at the transient diagram, the diagram, the time domain post-fault condition, and you see the way the curve oscillates before it settles at the steady state. So while the system is oscillating, that means the whole oscillation is bounded within the pre-fault condition and the post-fault condition. It never goes out.
Our oscillation comes from the inertia, يا سليمان ولا يا عمر. الانرشيا يعني when we clear the fault, the machine is accelerating here, right? This is the acceleration area. When we switch when we trip the fault, the machine will continue. If you are in a race and you are running here, and this is the end, what are you doing here? Before reaching the end, you start decelerate, and then you reverse your direction. You cannot, with this acceleration, you cannot directly reverse your direction.
Yes.
And you have here, when you trip the line, the machine will come here, but it will continue due to the inertia of the machine.
Okay.
But we started deceleration, so the speed will start decreasing. طبعا the speed here will be higher than 377. Okay. Here. But the angle will continue increasing. But since we have decelerating, then the angle will go back. And then it will not stop here from the first time, then we have inertia. And then it will continue up and down, and we have this overshot and undershot as we have here in the time domain.
Okay. Thank you.
Ayub Al-Horani, do you have a question?
Sorry, doctor, this is all under the condition that 90 degrees should not be exceeded, right? So the fault should be cleared before exceeding the 90. Otherwise, system will...
Here, no. This condition, no. The angle code, you can isolate the fault here, and then the angle can go, but it will go back. This angle can go up to higher than 90. This is the maximum angle, right? This is delta max. Okay? During the transient, delta max could go beyond 90 degrees. And there, at a steady state condition, and at this point is 28, so system is okay. If this point comes here, the initial, you are approaching the stability limit, so the stability of the system will be weak when you approach 90 degrees. And during the transient, the angle can go beyond 90. We have deceleration, so it will go back and forth. So it can exceed 90 degrees. This one can exceed 90 degrees during the transient. Is it clear, Ayub?
Yeah, clear, doctor. So the 90 degrees is not a stability limit during a transient.
Exactly, yes. Yes. Actually, if you want to explain more here, this fault probably in 520 you have been asked to get the critical clearing time and the critical clearing angle, right? In 520, if you have equal area criteria. So, as a matter of fact, this angle, delta max, can go until this angle. And the oscillation can reach to this angle. If it exceeds this angle, the system will be unstable. And now the angle can oscillate, comes to up to this point, and then go back and forth until it will reach to the final destination here. Right? But this is the maximum angle that we can reach. The corresponding clearing time will be called the critical clearing time. And if we wait for more time for the fault, then this angle will exceed the limit here and the system will become unstable. So in general, when you are talking about steady state operation, the angle shouldn't exceed 90 degrees. And during the transient, the oscillation could reach to up to this point, much higher than 90 degrees, 180 minus, you can see. يعني هنا 28. Assume that this is, yeah, of course, no, why we assume? We can have this, this is B electrical, and this B electrical we can equate it to 1 per unit, which is B mechanical, and you can get this angle. If we have this angle, you can subtract 180 degrees from this angle, it gives you this angle. So theoretically, the oscillation could reach to this point, and your system will be stable. Okay? Is it clear? You still have a question?
Thank you, Doctor. It's very clear.
Okay, thanks. طيب, let us move. For the comments, B mechanical is constant, governor is very slow, the steam change is very slow, so B mechanical is kept constant. At this steady state operating point, no acceleration power, B mechanical equal to B electrical. During a fault, after fault, it depends upon the rotor angle at that time. B angle, we have acceleration or deceleration. It depends on the scenario or switching scenario. It can also be seen from the bar angle curves that B mechanical equal to B electrical at 151, 180 minus 28. However, this operating point, as we mentioned earlier, it's not acceptable because it has a negative slope, unstable equilibrium point. This is unstable equilibrium point, as we pointed out before. You still have a question, Ayub? Or you forget to lower your hand?
Sorry, Doctor, I remove it.
Okay. The swing equation in all cases can be written as follows. Okay. Pre-fault, this is the equation of motion or a swing equation. Delta double dot equal to B mechanical minus B electrical pre-fault, and then this is B electrical during the fault, and then this is B electrical after fault. So these are the swing equation in each period, and in order to check whether the system is stable or not, you have to use integral, numerical integration techniques in order to solve these three equations within their time periods. This is numerical solution, and we have graphical solution, as we will see later on, for single machine infinite bus by equal area criteria. I think this is yes. Let me finish this part, and then we take the break for 5 minutes for prayer. In steady state stability studies with a small disturbance, the swing equation may be linearized for a small disturbance with little loss of accuracy. The stability can be checked through the characteristic equation of the linearized model, and this is the topic, the next topic that we will start, inshallah, today. In transient stability studies, the swing equation are highly nonlinear. Disturbance is very, very huge, or very nonlinear and abrupt change, big and sudden. So graphical solution equal area criteria is one of the two machine system. You can solve the swing equation using equal area criteria. For systematic way, you can have numerical integration methods such as Euler's trapezoidal method to solve the swing equation for each machine and multi-machine system. I think this we end this part, and let us take 5-minute break for prayer. It's now 6 o'clock, so 6:05 we will be back, inshallah. Okay. السلام عليكم ورحمة الله. So let us continue. If you have any question regarding this, okay, otherwise we can move to the next topic, which is bar system steady state stability of the bar system. Okay. Okay. In this part, we will, as we mentioned earlier at the beginning, we classify the bar system stability in general to three categories or three types: angular stability, voltage stability, and the frequency stability. Under angular stability, we have steady state stability, we have transient stability, and we have dynamic stability. So this is what we will address now: steady state stability. طبعا we will not say angular stability again and again, since the course is covering this angular stability specifically. So this is the steady state stability. We will see in steady state stability, as we mentioned earlier also at the beginning of the course, steady state stability means the system will regain its normal operating condition or steady state operating condition under gradual and small change, and the system can be linearized here. For steady state stability, system can be linearized, and when you linearize a system, you can apply the linear system. You can apply the superposition theorem, and you can also apply the what's called the second characteristic of a linear system, superposition and homogeneity. Homogeneity. Homogeneous system becomes homogeneous. That means, if you for superposition, you can, if you have different changes, you can study that the only one change at a time, and then you collect the responses together, and this gives you the complete response. The other one is the homogeneity. If you multiply by input, or if you scale input up for some values, and then in this case also the output will be scaled up with the same similar value. So we will study here zero input response and zero state response, and we can add them up to get the complete response of the system later on. So neglecting the damping torque, we will discuss each one under two cases. Zero input response. What is our input in this system? What is our input? When we say zero input response, what is our input? What do you think?
Load. Mechanical.
What is our input? Be mechanical. Be mechanical is our input. طيب, zero state, what is the state? What is the state here? Ramadan Ali, please.
It's the angle power.
It's what?
Power angle.
Power angle. So we will study the response of the system for steady-state stability analysis under zero input. And there is no change in mechanical power. Zero input معناها no change in mechanical power. And also no change in the angle. Zero state response. In both cases, we will consider the damping torque and we will neglect the damping torque. We will neglect it here and consider it here. Damping torque is B damping or T damping here, which is D dt, D delta by dt. Damping coefficient here, D, this is called the damping torque, without considering the damping in the swing equation, and also in other case we will consider the damping in swing equation. So in both cases will be considered under zero input and zero state. We will define here what we call synchronizing power coefficient, BS. What is BS? And what is the significance of BS? What is the, if you are given a value of BS, positive or negative, greater, bigger value or lower value, what is the significance of this? How can you interpret the synchronizing power coefficient? What kind of information this synchronizing power coefficient tells you? We will also see the time domain responses governed by natural frequency of oscillation. If you have, as we mentioned earlier here, in just that example, this is delta, and the fault occurs here, so delta becomes oscillate. So what is the frequency of oscillation? This is the period. So what is the frequency? How much is the frequency of this delta, ya shabab? If we draw delta versus T, and this is the case, what do you think the frequency of oscillation here? How much? عماد رجع في كلامه.
1 over T.
It is 1 over T, but how much the frequency? What do you think? يعني هل هو 50 60 related to this 50 or 60 ولا not related ولا ايه الحكايه؟
I think it is related.
يعني كام تقول يعني frequency؟
60.
طيب let us hear another answer. If anybody has different answer. The frequency of oscillation has nothing to do with the system frequency. The frequency of oscillation is frequency of oscillation for the stability studies. You can have it between 0.1 hertz to 3 hertz. This is the frequency of oscillation. Okay, so when you draw delta versus T, the frequency here is not 60. It has nothing to do with the 60 or 50 hertz. This is delta and also omega. The speed and the delta, or rotor angle and the speed and the rotor speed are mechanical quantities, not electrical quantities. And you cannot say the frequency of oscillation of delta is 60 hertz or 50 hertz, and also the speed. And these states are related to the mechanical part of the synchronous machine. These are related to the mechanical part of the synchronous machine. It is not current, they are not voltage to have frequency of oscillation equal to 50 or 60 Hertz. These are mechanical quantities related to the mechanical part of the machine, rotor speed and rotor angle. So we are talking about the frequency between 0.1 to 3 Hertz, frequency of oscillation. So we will see the natural frequency of oscillation, which is omega n 2 by f. And this 2 by f equal to, maybe if it is 0.1 this is 0.6 radian per second. If this is 3 و6 هنا تقريبا يبقى 18 radian per second. So this is the natural frequency here. So when you have this steady stability problem and you want to calculate the natural frequency of oscillation, this is the range of the natural frequency of oscillation. Damping ratio. How much is the damping ratio? Zeta. If you have the poles are here, so this cosine this angle gives you zeta. Cosine theta. If you have the poles here, complex poles as such, so zeta equal to cosine this angle. And if the poles are here, how much is zeta for these poles? How much is zeta?
It's 1.
It's 1. Do we have any oscillation here?
No.
Do we have any oscillation?
No, we don't have.
No. The response of the system will be as such. The response corresponding to these poles will be as such. The response corresponding to this pole will be second order with oscillation. And we have here J omega oscillation here. So this becomes the response of the system. Of course, if we have one pole here, then zeta equal to positive 1. Here zeta equal to positive 1. Zeta here equal to negative 1. And the response of the system will be unstable as such without oscillation. And if you have the two poles here, system stable or unstable, if these are the poles of the system, stable or unstable system?
Unstable.
Unstable with the oscillation. It oscillates, and we have here imaginary part, so the system will oscillate as such. It will be unstable. So we will define the damping ratio, how much of the damping ratio of the system, and also the third one, which is the damped frequency of oscillation, omega d. And omega d equal to, you can relate it here when you have an eigenvalue. When you have an eigenvalue equal to a lambda مثلا, equal to sigma plus g omega. This omega is called omega d. And omega n is square root of sigma square plus omega d square. Zeta equal to minus sigma over square root of sigma square plus omega square. So this is usually the time domain characteristic of the system response. And this is definitely covered in first course in control. So we will see for the steady state stability of the power system how to find these time domain response characteristics. Okay. So the steady state stability, we have a small disturbance, definitely small and gradual. It refers to ability of the system to remain in synchronism when subjected to small disturbance. It's convenient to assume that the disturbance causing the changes disappear and appear for some time and then disappear. Just a small disturbance happens and disappear. The motion of the system is free. The motion of the system is free. No extra damping or outside damping of the system. And you have this no control actions. You assume no control action, no excitation, and the governor control. No action outside the system. Synchronous machine is operating free. And the stability is assured if the system returns to its original state. And it's assumed that the automatic controls are not active. Automatic voltage regulator and governor. The behavior of the system can be determined in a linear. Since we have a small disturbance gradual, we can linearize the system, or linearize the swing equation specifically, system by examining the characteristic of the characteristic equation. We can linearize the system and we can get the characteristic equation. And based on the characteristic equation, you can get the pools or eigenvalues, what we call. And then based on the pools and the eigenvalues, you can judge whether the system will be stable or not. This is what we will do in this case. So this is the swing equation in general. We have here the damping term. And of course, we can convert this omega s to 2 by f. And this f is f0, اللي هو 60 hertz. 60 hertz. This synchronous speed constant. So h over 2 will go as 2, and then you have h over by f0, and yeah, it's just again, the oscillation of the angle has nothing to do with f0. ملهاش علاقة زي ما قلنا قبل كده. Okay. So if you steady state stability will be discussed in the following two cases: zero input response and zero state response. Zero input response معناها انه zero input. There is no change in mechanical power. And zero state, no change in the angle. We have a change here in mechanical power, but no change in the angle. So we will discuss both cases, and under, again, neglecting the damping torque and considering the damping torque. Zero input response, we will discuss it first under these two conditions. So let us go to the swing equation and neglect this damping torque, and then we can linearize and see what is how to check the stability of the system. So neglecting, but this is the swing equation. We neglect this part here, and then we can linearize. There is no change in mechanical power. And this mechanical power is constant, but this angle will change. Instead of having a delta, we will replace it by delta 0 plus delta delta. And we have here zero input response. So delta will be converted to delta 0 plus delta delta. If we have any change in this delta angle, so can we linearize around this operating condition? Can we, instead of having a delta, can we express this angle in terms of delta delta rather than delta? So this is very simple, straightforward. I'm quite sure you experienced such linearization in different courses. So we linearize the swing equation by around the initial operating condition delta 0. by considering delta equal to delta 0 by plus delta delta, and you substitute it here, and then we can write d square delta 0 plus delta delta over sine delta 0 plus delta delta. Of course, we will not keep this as such. Of course, you can distribute this d square delta 0 over dt square, d square delta delta over dt square, and you can expand this sign. Can you expand this sign here? Can you expand this term?
Yes.
Sine delta 0, cosine delta delta, cosine delta 0, sine delta delta. So this is sine delta 0 plus delta delta. So, and then we can, of course, do some, approximation. Then the delta delta is approaches 0. Delta delta is very small, a smaller change, very small change, and then we can approximate this cosine delta delta to be what? Cosine delta, if delta approaches 0, how much cosine delta delta?
1.
How much sine delta delta? If delta delta approaches 0.
Yeah.
How much? 0 ولا 0 ولا 0 or what?
It's 0.
Yes, 0.
It's not 0, but delta delta. Sine delta delta becomes equal to delta delta.
Tan. It becomes tan and delta, and then delta becomes delta.
لا, sine delta delta. If delta approaches 0, sine delta delta approaches delta delta.
Yes.
You can experience it if you have 1 degree. 1 degree equal to 1 times pi over 80 over 180 in radian, pi over 180 in radian. Okay. So check sine 1. How much sine 1? And to compare it with the angle itself here in radian. Delta delta in radian, definitely. And this value, you can see here how much this. It could be 0.1 something here. And this sine 1, it will be also 0.1. Same angle in radian. So sine delta delta approach is equal to delta delta, if delta delta is very small. But of course in radian, not in degree. So you can approximate, you can do such approximation in order to simplify this equation. And then we can move to the next here. We expand laptop, mute your mic, please. Still, Omar. Okay. So we expand here and we expand this term, and then we implement such simplification. Sine delta delta is very small. Since delta delta is very small, cosine approximately equal to 1, or sine equal to the angle itself in radian. So you can go back and substitute here, and you can write it as such. Initially, this term equal to B mechanical minus B electrical sine delta 0. And this also with this will go together. Now, at steady state, this equation can be written H over pi F0 B square delta over dt square equal to B mechanical minus B max sine delta 0. This is an initial condition at the operating point. This is valid. So this one will go with this B mechanical and this term here. So we end up with this d square delta delta equal to minus BE max cosine delta 0 delta delta. So we end up with this equation now. Since this is equal, then we have this equation. Then we have this. Okay? Type, can you get the characteristic equation of this differential equation that we have? Can we get the characteristic? Can we get Laplace transform for this differential equation to convert it to S domain, and then we can get the characteristic equation, and we can see the poles here or the eigenvalues? Can we do this? Yeah, of course we can do. This is S square delta delta of S, and this is constant definitely. B max is constant, and cosine delta 0 is constant, and then this is delta 0, a specific angle, and this becomes delta delta of S. So you can, of course, you can get it here positive, it doesn't matter, but you can write, this is the definition of the, but later we can go back to this one. Okay, let us define it here. And this coefficient is called the synchronizing torque coefficient. This is called BS. It's constant, B maximum cosine delta 0. It depends on the initial operating condition, delta 0. And this is called synchronizing power coefficient. Synchronizing power coefficient. So we can replace this part as BS. We will see the significance of BS now. So B max cosine delta 0 is simply the derivative of BE equal to B max sine delta. The dB by d delta equal to B max cosine delta here. So this is of course at delta 0. You can calculate how much it is, which is BS synchronizing at delta 0. Not delta equal to 0, but delta 0. Delta 0, initial value. So this is the derivative of the power with respect to delta calculated at this delta 0. Type, let me ask you, if this is the definition of the synchronizing power coefficient, what do you think the stability condition? يعني there احنا قلنا ان الانجل shouldn't exceed 90 degrees. Okay, this is in terms of the angle. طيب in terms of BS, if you are given BS 1 مثلا or minus 1, how can you check whether the system is stable or unstable here? Which one the system will be stable, which one the system will be unstable? Any idea? Yes?
If it's positive, then it's stable. If negative, it's unstable.
You are right. If BS is positive, then the system is stable. If it is negative, the system is unstable. If we define a BS as a derivative, so the BS is simply the tangent, the slope of the tangent of this curve, dB by d delta. So up to this point, which is delta equal to 90 degrees, the slope here is positive. But beyond the 90 degrees, the slope becomes negative. And as you mentioned, the point here is unstable equilibrium point, and here is a stable equilibrium point. So you can say the condition for the stability ان ال BS must be greater than or equal 0. يعني greater than 0. Okay? So this is the synchronizing power coefficient. It represents the slope of the tangent here of any point on the curve. So if it is positive, then we are below 90. If it is negative, then the system is beyond the 90 degrees and above 90 degrees, which is unstable here. So you are right, BS, if it is positive, the system will be stable. Otherwise, the system will be unstable. So we will define a BS as such, and we can write the swing equation as such. And the roots of the characteristic equation of the above second order differential equation is given by, you of course, you can convert to Laplace transform and do this. You can write here S square H over by F0 S square delta delta plus BS delta delta of S equal to 0. In this case, the characteristic equation, of course, will be, if you multiply this by F0 over H, so it becomes S square plus BS multiplied by F0 over H. So this is equal to 0. So this is the characteristic equation. If this is the characteristic equation, you can have S equal to S square equal to minus by F0 over H times LBS. And then you can get the roots here, S equal to plus minus the square root of this. Okay? Is it clear? So these are the roots for the characteristic equation. Muhammad Sir, please, if you have a question, Muhammad.
Please, can you repeat the last?
And you are up to here. Is it clear? Swing equation?
Yes, it's clear here.
Can you take the Laplace transform for this differential equation to get the characteristic equation? Take the Laplace transform. So this becomes S square, right? Delta delta. So you have here by over H over by F0 S square delta delta of S. Plus Laplace transform, this delta would be delta delta of S. So this is the equation now in terms of the Laplace transform on S domain. So you take delta of S as a common factor. So what is written here? By H over this S square plus BS. And of course, you can put it in the standard form. You can multiply both sides by F0 over H. So this becomes S square. And this coefficient will be BS multiplied by F0 over H. Okay, so it becomes S square if you multiply both sides by this coefficient. So you end up with this equation. Is it clear, sir? Is it clear?
Yes, it's clear.
Now you want to get the roots. So this S square becomes equal to minus by F0 over H times BS. And then you can write S equal to plus minus square root of by F0 BS. Of course, you can have here minus, if you take this minus, V minus 1, so you have here plus minus J. This is over H. So plus minus J square root of by F0 H times BS. So this is the roots now. And as you can see, the roots now are on the imaginary parts, imaginary axis. So this roots is 1, 2 equal to plus J times this value or minus J times this value. So these are the roots of this characteristic equation. And how much is the damping here? If these are the roots, how much is zeta? How much is zeta? If the root is here.
0.
0. Yes, you are right. And as you mentioned, zeta equal to cosine this angle. And this angle now becomes 90 degrees.
دكتور استنى.
هي ما هي جت دي synchronized. Both are synchronized. Time and also this mistake. Yeah. Okay, so delta here zeta equal to 0 for this. Okay, let us stop here and continue next class. If you have any question, stay. Otherwise, you can leave. And I would like, before leaving, I would like to urge you to select your